Okay, welcome everyone. It's a pleasure to have Khushraj Madnani as our speaker today. So Khushraj used to be a regular visitor to TIFR. He did his PhD from IIT Bombay and with Krishna, and his co-advisor was Professor Pandya, Paritosh Pandya. And now he's working at NPI Software Systems in Kaiserslautern. And Khushraj works on several areas of models of computation like timed automata and vector addition systems, and also logics like timed logics as well as Presburger arithmetic. So I think today he's going to talk about Presburger arithmetic. Thanks, Khushraj.
Thank you for the introduction, Shubhashish. So, good morning, everyone, and thank you for attending my talk on Quantifier Elimination of Presburger arithmetic and some applications of Presburger arithmetic. And so the main meat of the talk is actually the main result of our recent paper in ICAL 2024. And it's a joint work with Christoph Hasse from University of Oxford and Krishna and Homso Signature from IIT Bombay, and myself and Georg Zetscher from MPI Software Systems. I'll start with wishing everyone happy Teachers' Day. Okay, so the layout of presentation would be, I'll first start with Presburger arithmetic, its definition, and a little bit of history. And then I'll basically introduce the main crux of the presentation, the main result that I want to present. And then there's yet another problem statement, a dichotomy result that was published in FSTCS 2023 that I wanted to present, but that will depend on how much time we have while discussing. And finally, a very brief account of my research plans. And I urge you to please stop me at any point of time and ask me questions. It'll be as interactive as possible. So let's start with the history. So great people have great dreams. So again, we had this guy called David Hilbert and Ackermann, the student, and they actually dreamt, they hoped that they could actually automate the whole of mathematics somehow. And that's what they call the Einstein's problem. That means, so the problem statement was, or the challenge was, that was posed was that given any statement, can you prove the validity of that statement using the rules of logic? And I mean, of course, there were other interesting problems like the Hilbert's 10 problem, which was given a set of Gathen equations, which means a set of polynomial equations, where the solution does there exist an integral solution to those polynomial equations, and can you automatically find those solutions? So both these problems got related, and both of them was published in 1928 in Principles of Mathematical Logic, and both these problems were posed as a challenge. Moreover, they also hope that this is indeed true, that they could indeed find a terminated algorithm which can actually automate the whole mathematics. Tarski, he was interested, he liked the paper, and he said that let's be practical and let's start with a smaller fragment of material. And he gave this problem to his master student, Moses Presburger, and he gave this limited fragment. I'll shortly tell you what that fragment was. And he asked whether you can show the completeness and decidability and consistency of this particular fragment of a material. So within 2 months.
So when you say this fragment, like what was omitted?
That's what I'll say. So multiplication to decide was omitted. So within 2 months, this guy came up with a solution. And it was a positive solution. It was a ray of hope for both Ackermann and Hilbert. And he basically showed that first order theory of integers with just addition, comparison operators, of course equality, and standard axioms of arithmetic. So to be precise, it's linear integer. It's also called linear integer arithmetic. It's complete, consistent, and decidable. And the decidability proof basically goes via something called as quantifier elimination. So the idea was he basically given any statement, he could reduce that statement to a quantifier free fragment. And I'm actually kind of tweaking a bit. It's not exactly quantifier free fragment. He needed some more extra predicates that we'll discuss later. But somehow it basically eliminated all the quantifiers and then became just a Boolean combination of linear equations. That was known to be. But the dreams, of course, this was a piece for both Ackermann and Hilbert, and they actually till 1930 hope and in fact conjecture that there is nothing unsolvable in this world. But it's, in 1935, just 5 years from when their confidence was high, Church and Turing actually shattered their dream by showing that there are problems which are undecidable. And quite late, Markievicz, Robinson, Davis, and Putnam, they actually showed that even Hilbert's 10th problem is unsolvable. That means if you have the polynomial equation, you cannot find integral solutions to the polynomial equations in general automatically. And this is why the best you could do is kind of Presburger arithmetic. So the moment you have multiplication and you work on integer domains, you cannot solve it in general. So, but nevertheless, the rise and fall of this dream came up, resulted in a beautiful master's thesis. So this was indeed a master's thesis of Presburger, and this is what we are going to talk about. So, what is Presburger arithmetic? As I mentioned, it's linear integer arithmetic. So, it's a first order logic over the structure z plus less than 0, 1, which means that it has first order quantifiers, first order variables. The variables range over integers. You have addition, you have comparison operators, constant demand. That's it. So, you do not have multiplications. We have arithmetic multiplication. So, you can specify interesting statements like whether given number y is a multiple of 3 or some other number. So we can say phi of y is there exists x, y is equal to x plus x. This only holds for numbers which are multiple of 3. So, and then without loss of generality, we'll from this point onwards assume that the atomic formula of this form. So because it's integers, you can do some kind of standard manipulation, and you can assume that all your atomic predicates are actually of this, are linear inequality of this. Okay. Now, of course, this was not as expressive as the whole of number theory. It cannot encode the whole of number theory, but it will still encode interesting problems. And one of the examples is the Frobenius coin problem, which basically asks, given a coin of denominations m1 to nk, it's a pair of coins, what is the largest monetary value that cannot be obtained from these coins? And the solution is the smallest number satisfying this particular Presburger formula, which says that for any number y which is greater than the given number x, y is indeed the linear y is indeed obtainable from these denominations. So it's a linear positive linear combination of M1. So notice that, of course, once a number x, number n satisfies this formula, n plus 1 also satisfies this formula, n plus 2 also satisfies this formula. Now, the smallest number that satisfies this formula is indeed the largest number that cannot be obtained, right? Because after that, every number can be obtained.
So here, x kind of stands for this largest monetary value. This
yeah, the smallest possible value of x stands for the largest.
Right. Sorry, but don't you need some condition on x? Don't you need to say that x cannot be obtained from?
So that's why I'm saying smallest number. So if I say x cannot be obtained, I don't even have to put this constant. What I'm saying is, yeah. So if you say x cannot be obtained, then there will be unique solution to, there is only exactly one number that will satisfy this problem. That is the largest number that satisfies, right? But notice that what I was saying is, if you look at this x, right? If a number satisfies this formula, then the number plus one, and if n satisfies this formula, then n plus one also satisfies this formula, right? Because what does this formula say? That any number greater than this can be obtained by these denominations. So if all the numbers greater than n can be obtained, n plus one can be obtained. Now if we go back, and then the smallest number is indeed the one that cannot be obtained. Yeah. So if you say smallest number, you do not need to add that particular condition. But that's a good point. That you can add it and then you can do this first. Yeah. So to put the conclude the historical context, that since the decidability proof of Presburger himself, there has been a lot of work done in this particular domain, and now we actually have very sharp complexity results for satisfactory checking of Presburger arithmetic and its practice. For example, we know that full Presburger arithmetic is alternating the exponential time, so it's definitely between 2x time and 2x space. This was a result in 1980s by Madnani. And full PA with fixed quantifier iterations is between non-exponential time, non-deterministic exponential time and x space. It basically spans the whole of weak exponential hierarchy. This was by Haase in 2014. And existential Presburger arithmetic is indeed NP-complete. And this is quite trivial. It's basically using the techniques of integer linear programming. So we can basically reduce the problem to
basic question. Alternating 2exp time is not same as 2exp space.
No, so it's not exactly. We know that alternating 2x.
Alternating exp time, I think,
is exp space, but for this we don't. Right? Okay. And it also depends on. Yeah, we don't. And the idea is there is also parameter. This result is also parameters by number of variables. This I should have mentioned, but I did not. So it also basically spans the hierarchy between two external.
What is alternating 2xp time? What is 2xp time? There is no.
Yeah, doubly exponential time, and with alternating Turing machines.
Yeah, so the hierarchy on top.
Yeah. And now we will start with the main result.
So could you go back to the previous slide? So what is known right now? The best, that is like the complexity is between.
The best is the alternative extent. Okay. Right. So this is the best that is known. And of course, then you can use different parameters to get a sharper complexity result. That's what Haase did. Basically, fix the quantifier iteration, that became a parameter in the context.
But it's not like the number of alternate has to be some fixed finite number. It can depend upon the instance.
Yeah. So that is the first part. In this second part, the number of the number of alternation actually depends on the quantifier alternation. So it's one less than the quantifier alternation. So that is why this particular, the second part actually spans the whole of a weak exponential hierarchy. So yeah. So let's start with the story. Quantifier elimination. So what is this problem? So the problem basically says that given any Presburger arithmetic formula, phi y1 to y, so y1 to y, can we construct an equivalent formula phi prime without any quantifiers, without any other existence? That's it. Now, Presburger in general is not possible with Presburger. To be precise, it's not because of this integer domain. You cannot do that. But Presburger noticed that if you introduced some finitely many divisibility predicates, which are of the form x equal to y mod n, so that means x minus y is multiple of n, right? Then you can indeed, so if you extend your logic with this particular, these set of predicates, then you can facilitate, then you can actually do quantifier elimination. And that is exactly what he did.
So this does not increase the expressiveness of the original logic.
No, because this kind would actually be written existential one. But that's what we did, right? So it's y is the multiple of y is the multiple of 3, right? So this is something like this.
For fixed n features.
For a fixed term, yeah. So this is again for a fixed term. So he did not. So the m is constant. That is why this.
And this m, how do you get the value of the m from a given formula? So suppose if I'm given a formula, I want to remove these quantifiers,
Right.
eliminate the quantifier.
Right.
And from this given formula, I get the value of m. Like how do you get?
Right. So you need to compute it, and it's basically almost at most exponential. And there is so we will do the same thing here.
Exponential in the number of
In the size of the formula, input formula. So, so then the problem boils down to, given any PA formula, can we construct an equivalent PA formula with this extended divisibility predicates, which are not having quantifiers, right? So this is the problem that we'll be focusing on. And to give a historical note, as I mentioned, that the very first satisfactory checking algorithm was indeed via quantifier elimination.
But you would have directly then done it, right? Like given a PA formula, I mean, instead of introducing this modulo kind of those predicates, you could have directly converted, because this modulo thing can also be converted into existential.
So in some sense, you could see this as, this implies the result that as I said implies actually you are eliminating quantifier alternation rather than quantifiers, right? But it's still this result is, the implication is still weaker than what Presburger said, right? We are using the existential quantifier in a very restricted manner. We are only using the existential quantifier to encode the modulo constraints, right? And that's the whole point, right? So if you only care about satisfaction, then quantifier free fragment and existential fragment is all the same, right? Because somehow asking whether there exists a satisfying assignment has an innate existentially quantified block of points. And
So what are the predicates? Predicate does exist m such that x is congruent to y?
no, you cannot quantify anything. M is constant.
M is constant.
Yeah.
Okay.
So you can only say whether a particular number is divisible by a particular expression. In fact, you don't even need expression. You can say a particular x, single variable is right. So yeah, but the statistical pitching algorithm, the complexity was non-elementary, and the quantifier elimination procedure was also non-elementary. So it was very. Then about 4 decades later.
What is elementary?
Basically, any function that could be expressed in using teteration, exponents, multiplication, and addition. So elementary operators. So it's like Ackermann.
Ackermann is
no, it's primitive recursive. Sorry, sir.
Ackermann is non-elementary.
Yeah, non-elementary. Non-elementary, but it's even non-primitive recursive.
Even
Yeah.
non-elementary.
So this is primitive recursive. So yeah, so this was Star. Sorry. So elementary would mean that you only you cannot use teteration. Sorry. So you can use exponent, multiplication, and
addition.
Huh?
What in terms of Turing machine, what does that mean?
In terms of Turing machines, it's exactly the same, right? So the bounds. So if you
Oh, the bounds are
bounds are
so the runtime bound is
the
there.
runtime bound is exactly. So this is non-elementary. This and as I said, after 4 decades later, Cooper extensively improved this algorithm and gave a triply exponential time algorithm, right, for the full PA. And then after 3 decades later, there was no investigation going on. Of course, there were kind of approaches for giving a particular lower bound for quantifier elimination procedure. But the very first result, significant result, was by Weisfeind in '97, where he showed that indeed the triply exponential time is the best you could. It's optimal. It's the best you could achieve. And he also showed that it was like a corollary of this result that if you only restrict yourself to existential fragment of Presburger arithmetic, then you indeed need a doubly exponential law or doubly exponential time. So the idea is that quantifier elimination. So his claim was quantifier elimination for existential Presburger arithmetic formula in which doubly exponential.
Are these conditional results or are these unconditional statements?
A
A lower bound is a
conditional in the sense?
conditioned on something.
No, it's unconditional, right?
But you had like in one of the previous slides something like an NP complete for the existential fragment.
That's satisfiability checking. This is quantifier elimination.
Oh,
Right? So this is the point. Quantifier elimination is much more general than satisfiability checking. And that we see how geometrically.
The undecided gives a combination separation. So that has to be some condition.
Yeah.
I didn't understand
So
what.
like when you say something, it's so you say it cannot be below 2x time.
Yeah.
That implicit in that there is 2x time. Oh, but at that level maybe you have this because 2x time is
It's less than x time, right? So
yeah,
that's it.
because you're already the hierarchical.
Yeah, right. So
Sorry, what was the question? I'll tell you. So the question is where you say that something is in only this complex square and not in a lower complex square, then people are these two are different.
yeah.
But in this case, they are because of time.
That is, okay.
It is okay.
yeah. So yeah, you don't need the condition like B is not equal to P.
Yeah.
Yes. Okay. So why Q is interesting? The very first thing is powerful. If quantifier elimination is indeed possible, and any algorithm solving a problem P for a quantifier fragment can actually be lifted to solve the same problem for the full fragment, right? Why? Because you take the full fragment of PA, the general formula of PA, you apply a quantifier elimination, and then you already have the solution for quantifier, right? So if that is why it's much more general than satisfaction. Right. Secondly, its historical significance. It's very first algorithm for decidability of PA. It's not only that the quantifier elimination is a technique that dates about 200 years ago, right? I mean, since 4 years time, and it's also and that is why it's a fundamental problem in automated reasoning. It's not only limited to Presburger arithmetic. I mean, the decidability of first order theory of reals is also wired on confirmation. That's the most optimal complexity wise that we know. So,
But I mean, are there other techniques for? I mean, so when you say that any arithmetic solving problem people multiplied by 2028, there are possibly other techniques of going from a full PA to a quantifier free fragment or no quantifier. No, sorry, that's not.
so the best known technique is the Cooper's thing, right? That is a triply exponential law. Right. So for PA, that is of course for a theory of reals, you have this cylindrical algebraic decomposition and much more involved techniques. But then the moment you go, if your domain is reals, things become easier computationally, right? The moment things are at integer or discrete domain, you get.
So what is the decision problem for quantifier elimination?
Yeah, so the decision problem is given a formula, right? Can you construct yet? I mean, it's not a decision problem. It's basically what should I say? It's not a decision problem. It's procedure, right? So, given a quantifier free formula, can you construct a? Of course, we can. We know that we can. That's what the algorithm solves. But what is the most efficient way to construct a quantifier free fragment? That is the problem. And again, according to the claims, we think that almost everything is done because Cooper gave an algorithm, while Stein basically said that this is the best you could do. And the known algorithms for existential PA also are doubly exponential. So the Weismann's result basically claims that the state of the art is indeed optimal. So there is nothing to do. And that is where we have to differ. So our result is that quantifier elimination existential PA is indeed exponential time. And this is.
Sorry, then, okay, so this was the claim you were saying.
No, this was the proof, and we found the bug in the proof.
Okay.
So it was wrong. And in fact, this is also wrong. But the triple exponential rule. So this is also wrong. That is what we conjecture, right? At least the proof has to be corrected, right? The result might be correct, we don't know. But we conjecture that even the result is wrong. So we have a final analysis of this, but that's a future work. But to begin with, let's first restrict ourselves to existential quantifier. That's what we did in the talk. So
sorry, I'm getting a little confused. So what is the precise computational task? You are given a quantified formula in Presburger arithmetic. What are we supposed to do?
So you're given an existential Presburger arithmetic formula. So you're given formula with only existential quantifiers. And
Okay.
what you are supposed to do is you have to convert this into a quantifier free fragment of Presburger arithmetic formula, possibly with divisibility predicates. So you are allowed to use divisibility predicates.
Okay.
But that's it. So you have to eliminate all the existential quantifiers. That's
Okay.
it.
And you want to construct an equivalent formula without any existential quantifiers.
Yeah, exactly. Equivalent formula.
Okay.
Right. This is the problem statement. So, and this is to repeat. This is our result. Given an existential PA formula, we can construct an exponential size quantifier tree. PA formula with, of course, divisibility predicates in exponential. So why is this surprising? First thing is, of course, it corrects the wrong the mistakes in the theory, which was persisting since about 3 decades. But in spite of that, why is it interesting is even after almost a century of of the very first quantifier elimination algorithm, we did not know the best way to eliminate a block of execution. Right? So since 1921 until date, all the algorithms to eliminate a block of existential quantifier indeed needed doubly exponential. So it's a very fundamental, very basic problem. This is why it's surprising, and it's oblivious. So the problem is not that trivial. And the significance of our result. Of course, we do not solve the full quantifier elimination problem. We only eliminate the block of existential quantifiers. But it still has some certain significance. So it's similar to the previous ones. Any algo for a problem P for quantifier free fragment can be lifted for existential fragment. That's it. To be precise, in fact, more generally, any algo for solving a problem P with sigma 2k or pi 2k plus 1, where sigma 2k is there exists star for all star, exists star for all star, and pi 2k is for all star exists. Fragment can be lifted to solve sigma 2k. And for example, we basically using our result show that any formula. We basically show the problem of WQ testing. Now, what is the WQ testing? Any formula phi xy defines the WQ relation, a well-Quasi order relation. If and only if phi xy is reflexive and transitive, so it's a pre-order. And for any infinite sequence of vectors a1 to a1, a2, and so on, there exists I less than j such that ai and aj are related. So you cannot find an unrelated or infinitely increasing chains, right? Or sorry, decreasing chains. That's it. So now this is of paramount importance to theory of or verification of infinite state systems, because you can actually automatically check whether certain systems are certain infinite state systems are so-called well-structured transit systems, and we know that reachability for such systems are designed. So it basically helps in. Now it was already known that WQ testing for quantifier free fragment was QNP. In fact, it was QNP complete. And using our this and show that that for existential PA it's QNX. In fact, in our paper we also show that it's QNX complete. So we also give a lower bound result.
So this exponential thing, you were saying that when you were removing the existential quantifier, the formula that is the quantifier free formula that you get, it is exponential.
Right? That is why I get it.
So the input consists of phi.
Yeah.
And your question is is this phi defining a WQ relationship? That's what we need to decide.
Yeah.
And then you're saying that this can be written using only existential quantifiers.
Oh no. What I'm saying is the way we solve it. So there is a way that these guys solve it for quantified. So if you are given quantified Presburger formula, you can check it, check whether that particular formula is this or not. So using that as a black box,
Okay.
we can now do what? If you are given an existential PA, you just eliminate the quantifiers first, and then apply the result.
So this is an application of your result.
This is the application of that. Right. So this basically shows how general a quantifier elimination is. It's not as so satisfactory checking problem is just one problem that it solves. But there are other problems that quantifier elimination solves. It basically can lift certain problems that you know for a smaller class of logic to a larger class of logic.
Sorry, can you go back to the previous slide?
I think easily.
Let's go back to the previous slide.
Yeah.
That's right.
Oh, sorry. Yeah.
This is saying that, so what was the second point saying?
Yeah, so the second was what say. So sigma 2k fragment is a fragment which there exists are follows right? And because sigma 2k, the last block you'll have is there exists star. Right.
So that what this algorithm does is it doesn't do all existential quantifiers. They do
Just one block of this.
one block.
Yeah, exactly.
As in, like you're saying that this
Should I go to previous slide or this slide?
this slide is
Okay.
so this bird starts an algorithm which solves this big blow problem.
Yeah,
What
but
is-
only for quantifier frequent.
Oh, I see.
Yeah, so it's a QF version. of it.
Oh, I see.
Sorry.
Okay, that's what it is.
Right. And they actually left the existential
Sorry, can you go to the previous slide? So here, I mean, like this is basically saying that if you had the last block of quantifiers was a there exists quantifier, you can basically eliminate that block of quantifier by increasing your formula size by some exponential size.
Yes.
So wouldn't that mean that you can lift a problem from pi 2k to sigma 2k plus 1? Am I missing something?
Yeah. So the problem can be lifted, but the algorithm was the opposite way.
No, wait.
Does it go from sigma to go from sigma 2k to sigma 2k plus 1 or sigma 2k to pi 2k plus 1?
I mean, you'll go from sigma 2k plus 1 to pi 2k, right? Because if you see in sigma 2k plus 1, if you eliminate the last block of sigmas, you now have a formula that starts with a pi.
It's innermost.
Yeah, so it's now it looks like pi.
No.
Oh, you eliminate the innermost. Oh,
Yeah.
I see. Okay. Sorry.
Yeah. So last in the formula 3, it's the innermost block.
Okay. Sorry.
This was now. So we remove the inner.
So the output will remain the same, right? So the sigma remains sigma pi remains pi.
Right. Oh, sorry. So if there was some formula which said for all x, for all y, and no, sorry, there exists x, there exists y, and something else. So we'll remove the there exists y.
There exists pi together. It's a yeah. So for all x there exists. So if you have two quantifiers, you can remove a single block.
After that, there should be no other quantifier because there is
Yeah.
It's all quantifier free.
Exactly. And yet another problem is monadic decomposability. This problem is of interest to people in constrained databases, and the problem is very, very fundamental in nature. Basically, given any formula, phi of y1 to yn can be reduced into Boolean combination of formulae with just one free variable. So in some sense, it checks whether those free variables are indeed independent of each other or not. There's this notion of independence. And the QF version was again known by the same group Q1P, and of course we can do. So shall I proceed?
So what is phi prime here?
Some formulas,
Okay.
some set of formulas. The formula of the form, right? So basically, I just wanted to point out that these formulas just have one free variable. So yeah, so the problem statement given a formula phi y, there exists x. So now, for the sake of succinctness, we will basically replace a block of quantifier with a vector block. So there exists x psi of xy, where psi of xy is the quantifier should form, right? So without loss of generality, actually we can assume that the psi of xy is just conjunction of these. It doesn't have any negations or disjunctions. You can actually eliminate those using standard techniques. And hence, the problem statement basically is of this form. When you have there exists x, ax is less than equal to b by c, where a and b are matrices of appropriate orders, and c is the constant. Now, the main contribution of this paper is not it's not the proof. The main contribution is the insight of what kind of small model property. So we will now analyze and see why the classical small model property by Gathen and Sieveking cannot be used. And bear with me, and please, at this point of time, from this point till we reach the proof, please feel free to interrupt me anywhere you feel that because this is the most interesting part, in my opinion. So now, given this, suppose we are only interested in satisfying. So we have this formula, and we just want to know what are the satisfying assignments for this particular file. Right? Then that means we have to find an integral solution for x and y, right? And equivalent to find a solution for equation. So basically, your formula becomes your problem becomes finding an integral solution for a form of this for this form, right?
Okay.
And now this is where we have a classical small model property that can be employed, that is by Khushraj and Sieveking and Gathen and Sieveking. And yeah, so also notice that the solution to these kind of constraints is a polyhedral in general.
Sorry, what is a small model property?
Yeah, so that's what I will point out. Right? So now you have a b here. The vector b is the constant on that side. The small model property basically says that you can indeed there exists a b which is of the order of exponential in the size of a and b, such that if there indeed exists a solution in this polyhedron, then there exists a solution within the ball of radius d, right? So this is the small model. So if there indeed exists a model, then there exists a small model within this set.
So it's an upper. So you're saying if there is an integral solution, then there is an integral solution whose coordinates are not too large.
Exactly. Yeah. So that's the small model.
Depend on right?
It's fun. Yeah. Only if it's very easy, right? Because if you have a solution, then yeah. Now this is a classical small model property, and now let's see what's the problem, right? So now if you are interested in just quantified elimination, why can't you use the same idea for quantified elimination? Notice that your b in case of quantified elimination is by plus c. It's not a constant, right? So now, in some sense, you need a small model property which is robust to this parameter changing parameter b, right? But what happens if we change b in this case?
So it's something wrong. Sorry.
Yeah, no, please go ahead.
So you said that you can convert it to just a conjunction of linear inequalities.
Yeah.
But any such set is convex. And
Yeah.
But the original thing can describe things that are non-convex, and then you're only projecting variables. So how does it work? So how do you like something like x less than 2 or x bigger than or equal to 3?
Yeah, because we are only working on integers, we can do this. But of course, if you cannot do this in general for real domains or continuous domains.
Oh, because you are.
So you can always say x, say if you have a or b, right? Oh, the reason the or thing, right? The or thing you can always distribute your existential quantifier over or.
Oh, like you just.
Yeah, now we basically deal with them individually. That's it, right? Yeah. So sorry, I should go. Yeah. Okay. So yeah. So the moment you basically try to increase your b, this radius keeps on increasing, right? And now keep on doing this, right? So hence we will not be able to bound the region within which our small model lies, right? This is the reason that this classical small model property won't work for quantity. So we want something very different, and this is what we propose. So what our small model property says: if you have a b here, right, then I can actually, so there exists a constant d, which is exponential in the size of just a. So it is independent of b. It's exponential in the size of a, such that if there exists a solution there, then then there are some exponentially many bubbles of radius d, right? Or balls basically of radius d. And this exponential in just A, it's independent of B again, such that there exists a solution in one of these balls. So you don't care how far it is from the origin, but you basically find some finitely many regions where you have to search for your solution. Right? And now this model property is basically works as follows. Because all these parameters are independent of B, right? If you move the B, what will happen in some sense? These balls will move around. They won't change their size. They won't expand, they won't the number won't change, right? Their size won't change, they will just move around. Right? So in some sense, then the region that you want to search your small model, within which you want to search a small model, doesn't change. Its size doesn't change, its representation doesn't change.
There's some consider the shortest vector in lattice and
Shortest?
vector. So the AX is so the A is described the generator of a lattice.
Yeah.
But it's not exactly shortest vector now, but you have this coordinate wise constraints.
Sorry, I didn't get that.
So this question of like, so if you have a matrix of integers, so A is a matrix of integers.
Yeah, A is a matrix.
And AX will also so X will also be integer.
Integer, yeah.
So every such thing will like be a integer combination of the columns of A.
Yeah.
So that's the lattice generated by A.
Yeah, of
and
course. That's true. Yeah.
Problem of like giving on the length of the shortest vector in the lattice. And that often like so the thing is like those things also depend upon these kind of representation length questions that
kind of, but it's not exactly the same because
it's not the same.
Yeah.
But wondering if there is some connection to those and if those can.
Yeah. So no.
I mean, for a fixed B, this is if we fix a B, it's like fixing a cube in the space, and we are asking if there's a vector of the lattice inside the cube.
Yeah, something like that. Yeah,
Right.
Yeah. That's what I was thinking. That the less than equal to B should look like some kind of thing, and you're asking what is there a lattice point in that?
Yeah, but then the moment your B keeps on increasing, what your cube changes, right?
No, but the lattice, the fundamental domain is not changing, only the point.
Yeah.
Like the thing that tiles the thing. But I'm not saying that that will solve the problem. Just saying that like I was wondering if there's some connection to those kind of forms.
Yeah, maybe. Yeah, that's a good point. Yeah, but let's see how it is, and then maybe we can find the connection offline. Yeah, this is an interesting problem, question. So yeah, so what the small model properties? Let's be a bit more pedantic now. So the intuition was this, that now we have small model properties such that you can basically make sure that the representation of the small model doesn't depend on the B, on the function. It only depends on B. So now the idea is, given there exists x ax less than equal to b, let a be a belongs to n cross L. Let delta be some constant such that delta is equal to order of 2 is to poly a, right? And now this delta has something to do with a, so but I'm abstracting that information for the sake of reason. Now, if there is an integral solution for x, then there is one of the form capital D B plus D, where capital D is a matrix, is a rational matrix, right? Of the form of n cross L, and the small d is a rational vector. And the bit, so this basically represents the bit representation. So the number of bits that you need to represent D is less than equal to delta. It's not exact number of bits. The number of it basically shows the maximum number of numerator and the denominator. The maximum number of the numerator, max amongst the numerators and denominator of B is less than equal to delta, and is the same.
So the bit will be polynomial.
Bit will be polynomial, exactly, because you log of this, right? Yeah, because we're interested in a bit stronger statement that even if you give a binary encoding, you get only an exponential blow up in unary encoding.
Yeah.
So that's it.
So here both the capital D and little d can depend on B.
No. Capital D and little d does not depend on B. That's the idea. So, it can depend on B, but you don't care, right? Because in some sense, if you bound, so there are only finitely many possibilities for D and A, right? Because you're bounding individual entries of B, right? So now, even if it depends on B, if you really want to change your existential quantifier and remove your existential quantifier, what you could do is you could basically disjunct over all these finitely many possibilities, and then you can replace your existential quantifier with finitely many disjunctions. So even if it depends on B, it doesn't matter because they are bound. They're only boundedly many possibilities for B.
And for the sign of the bound matters because you want to put the next time.
Exactly, size of the bound matters. So that's why the delta is an exponential, right? So yeah. So now using the small model property, it's trivial that you could this actually implies solution to our problem, right? Why? Because your formula was of the form there exists x ax less than equal to by plus c. Now just replace your small b with by plus c. So basically replace your x with b of by plus c plus d, right? From using the small model property. And then what you want is that you iterate over all the possible d's and d's. That's what you asked, right? So if you iterate over all the possible d's and d's pair, so and though they're only finitely many such exponentially many such pairs. And additionally, you also have to check because you are working on Presburger arithmetic, you need to check whether you are within integral domain or not. So you need to check whether this d by plus c plus d, the amount, the expression that you are replacing your x with is indeed an integer. And this is where you need your modulo or divisibility constraints to input this particular constraint. Right? So that's it. So given this formula, you can basically get a quantified formula, and hence it suffices to prove this formula. Now,
How is that constraint encoded as a W? So you basically pick some large M and say.
so yeah, so suppose you have a denominator here somehow, right? So you basically pick a large denominator, right? You have a bound of denominators anyway. Pick the large denominator and just check whether your numbers are divisible, basically, by that denominator. That's it. So hence it suffices to prove the small model property. So I'll not prove the small model property again formally. I'll just give an overview, and the overview is quite abstract. So as I said, the solution that you are looking for is the polyhedron, right? Now, for a given B, the first step is to show that for a given there exists a matrix Di such that Di is within these bounds, within this delta bound, and Di of B is equal to Ri, where Ri is a solution to this. So basically, there exists amongst these these big D's, which is less than equal to delta, you can actually find one of the D's such that when you transform your B with that D, you get a solution for this, but a rational solution for this, but not necessarily integer, it could be rational. But in fact, it's a bit more stricter. In fact, there will exist a D such that you get a rational solution on the minimal face of this polynomial. So this is the very first solution, first step. And now once you have this rational solution, this Ri somehow actually corresponds to the center of the bubbles that we saw before. So for all these Di's, you get a corresponding Ri, and these Ri's are the bubbles that you were looking at, the exponentially many bubbles that you saw. Okay? I mean the center of the exponential. The second step is to show that if there is an integral solution to this set of constraints, then there is one of the form one which is closer to this matrix. So which means that if you have an integral solution, then there is one integral solution which is close to this rational solution. Every rational solution. And close means how close, and that is delta, same bound that we have. And hence you are done, right? Because that's what we wanted. So yeah, so that's what we wanted somehow. That can you find a bubble within which you can find a solution? That's it.
So can you just, what is the first step again?
So first step was to find the center somehow. To be sorry. Yeah. First step was to find the center of that bubble. So the center of that bubble is that rational solution which is within is one of the rational solutions of the game. It could be rational, it could be integer, but one of the rational solutions, right? And that which could be obtained by this small transformation, the di transformation from E, right? So that was the first step.
The image seems to be shown two, like a di and a dj.
Yeah, so dj is not the correct one, and then you have to choose one of these d, one of the d's, right? And then you choose that di, and successfully you'll find you're bound to find one of those dis. If indeed there is a solution, then you will find one of the dis which will take you to that solution from B. So that is the first step, and the second step basically says that once you find the center, right? And if you indeed have an integral solution, you have one close to every rational solution. So you have one close to that, one within that ball. And that's it. And I think how much time do we have? 5 minutes?
10 minutes.
10 minutes, right? I'll just wrap up. So this is basically the main crux of the result. And now I'll basically give one more application of analysis of Presburger arithmetic, which I indeed like. It's a very nice dichotomy result based on counter machines. So what are counter machines? I'll just quickly browse through it, and I can take this movie. So counter machines are extensions of automaton. You have finitely many states or control states, and you have some finitely many counter variables which can take any integer value, any positive integer value, non-negative integer value. And then what you can do on a transition is you can increment with a particular constant, decrement a particular counter with a constant, and you can check whether a counter is zero, right? So this is basically the model of counter machine.
So the counters will never the counters are always non-negative.
Always, so non-negative variables. Yes. So, for example, if you start with all the counters being 0 and choose it as initial state, what do I mean by 1? 1 is it's a 2-counter machine. By 1 1 I mean that increment both the counters by 1. -1 0 I decrement the first counter by 0, and 0 2 means I increment first counter. That's it. So the run would be something like this. So you can take this 1 1 and increment both the counters. So Q1 1, Q2 2, Q3 3, and so on. Then at some point of time you can choose to choose to take this loop between Q0 Q1, where what will happen? You will decrement C1 counter C1 by 1, but increment C2 by twice. So the slope of C2 is going twice, and then at some point of time when C2 is equal to 0, you can basically exit to the Q2, which might be a halt condition of the requirements, right? And then you stop at Q3 is equal to 0 3.
C2 can never be 0.
Sorry?
C2 will never become 0.
Oh, sorry, this is C1. Yeah, good point. Yeah.
So what is the what is the accepting statement? Like what?
Oh, yeah. I mean, the idea is the accepting state is always given to you as a part of the problem. That is one of the variants, but the other variant is accepting state, like or a halt state, can actually be given as a part of your model itself. So there are various definitions, right? So what we are basically looking for, in our definition, we basically want to be made much more general. And the accepting condition is actually a configuration that you want to reach, or a set of configuration that you want, right? So, and now just to point out, what are reversals? A point in a run where one or more counters switch from increasing mode to decreasing mode is called a reversal. Right? This is a reversal. There are no reversals in C, right? So now the reachability problem. So what is the reachability problem? Given a counter machine M, a configuration C. So now C becomes a part of the accepting state becomes a part of the problem statement. Can you reach the configuration C beginning from initial state?
Sorry, the silly question. Should I think of it as some sort of generalization of like DFAs or something, or is this incomparable like counter machine?
You can see this as generalization of DFA, definitely, but it's a very strong generalization of DFA. These are very complete models. These are undecidable. Yeah. So yeah, so it's undecidable, as I pointed out. Hence, various restrictions for getting decidability is being explored, and one of those was reversal boundedness. The reversal, as I mentioned, is the point where your counters mode go from increment to decrement. And Ibarra in 1980s basically suggested this restriction, and he showed that if you bound all the runs of the reversals in all the runs of your given counter machine, then the reachability becomes decidable. And
It means that given a counter machine, you can say that no k reversal run can reach this configuration.
no k reversal run can be
There might be
k plus one reversal. This is one model. The other, when this was actually, these are equivalent in this particular definition. But when Ibarra suggested, he suggested the definition of k reversal bounded. It's a semantic subclass of counter machine where all the runs are k reversal bounded. So there are no other. So there are no k plus one runs existing. Yeah, exactly. There are no k plus one runs in the model itself. You cannot generate it. Right.
This is a property of the counter machine itself.
This is the property of the counter. The semantic property of the
Restriction of the counter.
Yeah. So
in that model, if you have a counter machine in which k plus one reversal runs are possible, then you cannot say.
yeah, we cannot say anything because that doesn't lie within the purview of our input. So generalizing, so our task or our contribution was generalizing reversal bounded to reversal infrequency. And as the name suggests, what we do is given a counter machine n and a monotone function from n to n, we say that the counter machine is f reversal bounded. Right? If and only for any run R of the counter machine, number of reversals in R is bounded by f of R, f of the length of R. So a number of reversals are bounded by some function of the length of the length of, right? This is basically the model. Now notice that every machine is f reversal bounded for f1 at time is equal to 1, right? Because we can never do this. So linear is not interesting, right? Even if you have n by 2, you can add some dummy states in between and you simulate the whole, right? So we say that f is essentially bounded. The function f is essentially bounded for counter machines. If and only any f reversal bounded counter machine is also constant reversal bounded. So suppose if you can find a function f such that if you bound that if you say that this particular counter machine is f reversal bounded, then it is indeed a constant reversal bounded. Then we said f is essentially bounded for counter machines, right? Which means f reversal bounded does not exist in that true sense, right? Because it's indeed a constant reversal.
So the constant is the one by Ibarra. Constant reversal bound. The k bound.
The k bound is the one by Ibarra, right?
And that is the same as constant reversal.
Yeah, and that So there exists a k, so that's k reversal bound. Right?
This is the same as saying that any loop, for example, doesn't have a plus one and minus one for the same counter.
Any loop doesn't have a plus one and minus one for the same counter. That's for the constant reversal bound. That's what you're saying, right? Yeah. In some sense, it implies some of that, right? Because it also implies some kind of flatness condition. So what you're saying is, I think, a flatness condition that within a loop you cannot. But within a loop, if you have.
What's an example of a f reversal bounded where f is sublinear?
Where f is sublinear. Okay. We have it. But it's
We can do it.
We can do it.
With constant.
Huh?
No, not constant. I mean,
And then I think when I give you the dichotomic theorem, you will appreciate the.
Okay, sure.
Okay. And so now the problem reachf is basically the reachability problem for f reversal bound function. The input is the f reversal bound counter machine and the configuration C, right? This is the input. And the output is scan the given counter machine. Given that, so it's a promise problem that you are given a counter machine which is f reversal bound. So you already give a promise that and the configuration C. Now, can you reach this initial this from initial, right? This configuration.
And what do you assume about f?
No, so the f is parameterized. So for what happens with your f changes, that's the analysis that we do. Right? So the main result is this. This is a dichotomy that I'm talking about. So for any monotone function f, one of the two is the possibility. Either f is essentially bounded for counter machines, right? Which means LCD, or F is at least logarithmic, right? In which case, reach of F is undecidable. So, which means that if you consider for the class of F reversible bounded quantum machines, where F grows at either equal to or faster than logarithmic function, then it's indeed undecidable. You can actually simulate the real quantum machine. So there indeed exists a logarithmic quantum machine because we basically create gadgets to simulate which are logarithmic reversal bounded, but which simulate any arbitrary quantum machine.
And there are no log n reversal bounded.
That's the word. Any log n reversal bounded is indeed
Essentially.
So that is the right.
And essentially, the result is decided.
Is anyway decided. And that is the idea. So for this, what we do is we basically show that an FRB machine can simulate, or log RB machine can simulate arbitrary K quantum machines. That's the main idea. And to show, sorry, what happened? Oh, and the first one is basically shown by analysis on Presburger. So what we do is, in the reversal bounded, so if you have a reversal bounded run, right? That run, the relation between the initial counters and the final state, the value of the final state, the counters of the final state, is actually definable by Presburger. It's semi-linear. Semi-linear relations are actually equivalent to Presburger definable relations. I'm not going to detail what semi-linear relation, but it's you can find a Presburger formula. It's a quantified Presburger formula that can do this. And then what we show is if you keep on iterating this, right? Yeah, sure. So this is the last slide. So if you keep on iterating this, the growth of the run basically with respect to reversals is at most exponential. You cannot doubly exponential. So that is why you do not get a log kind or sub-logarithmic. And that's it. And about my research plans, about these works, I want to study quantifier elimination for Presburger arithmetic for fixed quantifier eliminations. This becomes a parameter. And we believe that you can again get a hierarchy between 2x time and 3x time. Sorry, 2x space, the alternating, and explore emptiness for Turing machines with infrequent results. So, same trick for Turing machines, where the read-write header only moves left and right infrequently. And yeah, and in general, when such works are divided into three parts: formal logics and automata for time systems, network control cyber physical systems, and formal logics and models of computation. So I'll be happy to talk about any of these if you are interested. And my future research in time systems, the main thing which I would want to, which would be of interest to the public is this: that you want to characterize precisely the complement closed languages definable by time. So timed automata are automaton with clocks and extended with clocks, which you can reset and check for. And we say that it's not closed under complementation, but we want to give a machine calculation. In logics, we already discussed that the main is study of Turing machines with infrequent reversals and generalizing our quantifier. That's it, and I'll be happy to take questions.
Questions? So at what point does it start becoming interactable? Suppose I'm bounded by degree 2 instead of linear. What can you say about that? The first thing you said about the quantifier elimination.
No, so instead of linear arithmetic, the degree. I don't have an answer for that. So yeah, I don't.
I mean, is it clear what quantifier elimination means over there? Like for linear, you're replacing there exists with these.
Yeah.
Is there some tool over there which?
No, I don't think so. It admits a quantifier elimination to begin with, if I'm not wrong. But I mean, again, I don't know about that. Because it's undecidable. I think, yeah, given thought of working and finding this philosophy. But for rationals, of course, there exists one polynomial. The theory of reals with multiplication and addition. I mean, there is already a quantifier elimination procedure using cylinder.
Other questions? So I'd just like to mention that Khushraj is here today as well as tomorrow, and I think there are several free slots tomorrow if anyone wants to meet to come. Okay, so if there are no more questions, then let's end the speaker.